Okay, so today we're going to start with Lewis dot structures for ions. Okay, so the first one we're going to draw is sulfite. Where could you find the formula for sulfite? Where could you look? If I wasn't here to help you, where would you find this formula? You remember your good old naming chart? Good. Okay, naming chart. Could you also just Google it? Sure. Okay, so first thing, you just need to have the formula. So sulfite is SO3 with a -2 charge. And then we're going to follow the same process we followed before. So we're going to count valence electrons. How many valence electrons for sulfur? Okay, 6. How many for oxygen? Okay, 6. And how many oxygens are there? 3. So I'm going to multiply it by 3. And then this is the new part. So the ion has a -2 charge. Is there 2 extra electrons or 2 fewer electrons? 2 extra. So we're going to have to add 2 to our total count because of that -2 charge. All right, so we should have a total of 26. Okay, this is the only new step. Okay, so if it's a -2 charge, you just have to add 2. Then from this point forward, it's pretty much the same. So which atom do you think goes in the middle? Okay, so S goes in the middle. And then I'm just going to space out the O's. Okay, so we started with 26. How many electrons were used in the single bonds? 6. Okay, so we've used 6. So there's 20 left. So now we just go through and make sure every atom has 8 valence electrons. Always start with those outer atoms. Okay, so oxygen has 2 here. So how many dots do you have to draw? Okay, 6. And all of the oxygen should be the same. So I'm going to give 6 to each oxygen. Okay, so we used a total of 18. I have 2 left. Where are those 2 going to go? Okay, sulfur, right? Sulfur has 2, 4, 6. And how many does it want to have? 8. So how many do you have to draw? 2. Okay, have we used up all of our electrons? Yes. Does every atom have the filled octet? Good. The last step, because it's an ion, we put the structure in brackets, and then you just put the charge outside. Okay. So that's just how we know that it's the ion and it's not like a neutral compound. Okay, any questions so far? Okay, let's look down at nitrate. So nitrate, it's similar, and then there's going to be one extra step on this one. Okay, so nitrate has a formula of NO3 with a -1 charge. How many valence electrons does nitrogen have? Okay, 5 for nitrogen. How many for oxygen?
6.
6, and how many are there?
3.
3. So I'm going to multiply that one by 3. What does that -1 charge mean? Okay, you need 1 extra electron because it has a -1 charge. So how many total electrons?
24.
Okay, so 24 electrons. Now we're going to draw it. Which element goes in the middle? Okay, so nitrogen's going to go in the middle. I'm going to spread out the oxygens. All right, so we started with 24. How many are used in those 3 single bonds?
6.
Okay, so how many are left over? Okay, 18. This oxygen has 2, so how many dots do you have to draw? Okay, so each oxygen needs 6. So I'm going to draw 6. Okay, I use 18 Is this a good structure?
No.
Okay, what's wrong with it?
Nitrogen doesn't have any.
Okay, nitrogen's missing some electrons. It has 2, 4, 6, but how many does it need?
8.
8, so I'm short 2. So what should you think if you're short?
Double.
Okay, double bond. So erase one of your lone pairs, turn it into a double bond. Okay, new tally. So I started 24. I now use 2, 4, 6, 8. I should have 16 left. I've used 2, 4, 6, 8, 10, 12, 14, 16. Okay, so this time, does every atom have a filled octet?
Yep.
Okay, did we use all 8?
Mm-hmm.
Last step, what do we have to add to
The
show?
ones.
Okay,
Brackets.
add your brackets. Okay, how many of you put the double bond here? How many of you put it down here? How many of you put it over here? How do you know where to put the double bond? Does it matter?
No.
Okay, it doesn't matter. In real life, the double bond constantly moves. Okay, atoms, they don't have brains, so they don't pick and choose like where the double bond goes. So for an instant, the double bond will be between those two atoms. Then electrons are constantly moving, yes? So then in another instant, the double bond will move between these two atoms. In another instant, it'll move between those two.
Try to find equilibrium.
Yep. So they constantly move. So when you have this sort of situation, we call this a resonance structure. Okay. So I'm going to change the slide and then we'll talk more about it. So resonance structures are when there's 2 or more valid Lewis dot structures. Okay. So this example, carbonate, it's just like the one that we did. Okay. So you could have the double bond here, you could have the double bond here, or you could have the double bond here. Are all 3 of those good Lewis structures? Okay, so when you have a resonance structure, when you draw it on paper, you just have to draw every option. So instead of drawing 1, you would end up drawing all possible options. So you would draw 3. And then what do you notice in between them? Do you see like the double-sided arrow? Okay, so in between you have that double-sided arrow, just showing that both of those structures are valid. Okay, this one shows both of these are valid. Okay, so resonance structures are, if there's multiple correct Lewis structures, you have to show them. Okay, so we're going to draw out the Lewis structure for ozone. Ozone is O3. How many valence electrons are in oxygen? 6. And there's 3 of them, so how many total? Okay, 18 total. Ozone is just 3 oxygens. So we just do 3 oxygens bonded together. Okay, we started with 18. How many did I use on those single bonds? 4, so there's 14 left. I'm just going to start on the outer atom. How many more electrons does this one need to get to 8? How many are here? 2. So how many more do you have to get to 8? 6. So I'm going to give this one 6. I'm going to give the other end 6 because they're identical. So I've used 12, so I have 2 left. If I put 2 on this central oxygen, is that good? Okay. Is that a valid Lewis structure? Okay. No, what's wrong with it? How many valence electrons does the central oxygen have? 6. It has 2, 4, 6. And how many does it want to have? 8. So I'm short. So if you're short 2, what should you be thinking? Okay, double bond. Oops, I meant to erase. Sometimes I can't erase if I take too long. Okay, I'm going to change my color. I'm going to draw it over here. Okay, so you're going to draw your double bond. 6, so I have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, if we add a double bond, does that change everything? So now, do we have a filled octet? Okay, how many of you put your double bond between these 2 atoms? How many of you put them between those 2? Okay, in reality, Does that double bond move between both? Okay, so we're going to draw the Lewis or the resonance structure. So that means you have to draw both options. And for those of you who feel dramatic and you're like, oh, I have to draw another one, how many seconds did it take me to draw it? Probably less than 4. Okay, so once you do the first one, you just copy for the second one and make the mirror image. So does writing the second one really take that much time? No. Okay, it doesn't. It happens every year though. People get really dramatic when they're like, I have to draw another one. But did that really take like 5 seconds or under? Yeah. Okay, so is it the end of the world to have to draw a resonance structure? Yes. No, it's not. The last thing we're going to talk about are just exceptions to the octet rule, okay, the rule breakers. So we're going to talk about 3 rule breakers. The first one is if there's an odd number of valence electrons, you're not going to fulfill the octet rule. Okay. What number does the octet rule represent? Okay, octet is 8, and is that an even or an odd number? Even. So if you have an odd number of valence electrons, are you ever going to get to an even number? No. Okay, so if you have this sort of situation, the octet rule has to be broken. So let me show you an example. Nitrogen dioxide is an example. Okay, so we're going to count valence electrons. How many valence electrons does nitrogen have? 5. Okay, 5. What about oxygen? 6, and there's 2 of them. So how many total? Okay, 17. So everyone focus here for a second. So if you're adding up your valence electrons and you get an odd number, the first thing you should do is go back and double check your math. Okay, this doesn't happen very often. So like 98% of the time, if you end up with an odd number, it's because something's incorrect over here. Okay, so you're going to go back, you're going to double check things. Okay, if you double check it and you know it's an odd number, then you're just going to move forward, but know that that octet rule, it's going to be broken. Okay, between nitrogen and oxygen, which one's going to go in the middle?
Nitrogen.
Okay, nitrogen goes in the middle. Okay, so we've used 4, so there's 13 left. How many electrons do we have to draw around the oxygens to get them to 8?
6.
Okay, so I'm going to give each one 6. So I used 12, which means I have how many left?
1.
Okay, so that 1 is going to go over nitrogen. How many valence electrons are in this picture?
5.
Okay, it has 2, 4, 5. And how many does nitrogen want? 8. Is 5 far from 8?
Mm-hmm.
Okay, we're going to break the octet rule because it's an odd number, but can we do better than 5?
Yep.
Okay, so if we can do better than 5, we have to do better than 5. So what could I do to get this closer?
Double bond.
Okay, a double bond. So I'm just going to erase one of those lone pairs and I'm going to make it a double bond. Okay. So here I've used 2, 4, 6. And then I've used 2, 4, 6, 8, 10, 11. Okay. So I've used all of my electrons. Now how many valence electrons does nitrogen have? Okay, now it has 2, 4, 6, 7. Is 7 as close to 8 as we can get? Mm-hmm. Okay, so this is the best we can do with our Lewis structure. And there's something else about this one. What other kind of structure is this?
Resonance.
Resonance, so what do you have to draw? Okay, draw the resonance structure. Time yourself. How many seconds did it take?
That's like 3 seconds.
Like 3. So is it a big deal to do a resonance? Okay, no, don't make it a big deal. Okay, rule breaker number 2. They are the electron deficient atoms. What does deficient mean? Less than. So a couple atoms can be electron deficient. So boron and beryllium are these exceptions. They can get by with 6 valence electrons. Okay, so instead of wanting 8, they can be stable with 6. So I'm going to show you just an example. I have beryllium trihydrate, so BeH3. How many valence electrons for beryllium? 2. I need an extra electron. Let's make it boron. Let's make it, hold on. Let's go boron trihydrate. So let's go BH3. Okay, how many does boron have? 3. How many does hydrogen have?
3.
Okay, so 6 total. So boron is going to go in the middle in 3 hydrogens. Okay. I had 6. I used all 6. Is that okay? Okay.
Yeah.
It has to be, because do I have any more electrons? Okay, will double bonding fix anything? No, hydrogen can't double bond. So a couple of these can be electron deficient. So if you see boron or beryllium and you only have 6, it's okay. All right, and the last one are some elements can have an expanded octet. Okay, so expanded means they can have more than 8. So some elements can have like up to 10 or 12. Some common ones are phosphorus, sulfur, silicon, and chlorine. However, there's more. Okay, it's pretty much the third row down. They can have more than 8 in their valence shell if they need to. Okay. So I just want to do 2 practice Lewis structures for expanded octets. Are you all okay if I change this slide? Okay, first one is PCl5. How many valence electrons for phosphorus? Okay, 5. What about for the chlorine? 7. And how many are there? Okay, so how many total for PCl5? Okay, 40. Which atom's going to be the central atom? Okay, phosphorus is going to go in the middle. This time you know you're going to break the octet rule, because how many chlorines do you have to add? 5. So you're just going to like try to evenly spread out those 5 chlorines. Okay. So if you see something like PCl5, you know you're breaking it because you got to fit 5 around the phosphorus. So we started with 40. How many did we use in the single bonds? Okay. We used 10, so there's 30 left. How many dots do you have to add to each chlorine to get it to 8?
6.
Good. 6. There's 2 here, so I had to draw in 6 to get it to 8. So I'm going to add 6 to each chlorine. Okay, which is exactly 30. So I've used all my electrons. Is chlorine, do they all have 8?
Yeah.
Okay, so chlorine has fulfilled the octet rule. Phosphorus has 10, but is that okay? Okay, so sometimes we can break the octet rule. Okay, ready for the last example? Okay, let's do one last one. XeF4. How many valence electrons in Xe? It's going to have 8. It'll have 8. How many in fluorine? 7, and there's 4 of them, so how many total? Okay, 36 total. Which one is going to become your central atom?
Xe.
Okay, xenon goes in the middle. The fluorines are going to go on the outside. All right, so we start with 36. How many have we used on the single bonds? 2, 4, 6, 8. Okay, we've used 8. How many are left? 28. All right, fluorine has 2, so how many dots do you have to draw to get fluorine to 8? Okay, so give each fluorine 6 dots. Okay, so everyone look up here for the moment. So let me show you what's happening. So we filled the octet rule for all of the fluorines. That took up 24 electrons. So how many are remaining?
2.
4. We have 4 more. Do you have to place them?
Yes.
Yes, they have to go somewhere. If an atom's going to break the octet rule, it has to be the central atom. Okay, so you can't just like put them in the fluorines. It has to go in the central one. And they stay as a lone pair. So I'm just going to put like a lone pair on one side of xenon. I'm just going to spread them out and then like a lone pair on another side. If you chose different places around xenon, like if you put it here and here, is that okay?
Yeah.
Sure. Make sure you keep them as a pair though. Okay, so these extra 4, they have to go somewhere and they're going to go on that central atom.